Okay, so my name is Lynn Schreyer. I'm a professor in the Department of Mathematics and Statistics, and I'll be talking about a project that I built up from a semioid project that seemed to go over really well with students who are taking a first semester differential equations class. So this course that we teach at Washington State, just as to give you a perspective, Pullman campus has roughly 16,000 students, and Math 315 usually has 3 to 4 sections per semester with 60 to 90 students per section. So these are pretty large classes. The textbook we're currently using is Lebel's Notes on DiffEQs, which is free, so that's nice. Okay, so where I got the idea for the project was from Semioid Differential Equations by Bryan, and it's on using a spring mass dash pod system to model essentially a one-story building subject to an earthquake. So you have a foundation and you have a one-story building, and as the foundation shakes, eventually you reach the natural frequency and you can see what happens. One of the tricky things is to go from this horizontal system here and going to a building, because it's not like really clear where the spring is in the system, but the spring is such that it always is trying to restore the mass to the center. Okay. So what I wanted to focus on was to give them some understanding of what the modes are in a system of first order linear differential equations. So this is an end of semester project, and the order we usually cover, okay, sorry. We usually cover systems of differential equations towards the end of the class because a lot of students are taking linear algebra as a co-requisite. And so we move everything else so that we can cover systems of differential equations towards the end. And I do not cover non-homogeneous systems of differential equations. I figure that if they need it, if they understand how to solve nonlinear second order a single differential equation, it wouldn't take much to get the idea of how to find analytical solutions for non-homogeneous systems. So we get to the point where we're studying homogeneous with constant coefficients, solving it with eigenvalues and eigenvectors, and then vector fields for two-dimensional systems. And then the second to last week of classes is when we start the project. So we start this project in class. Usually I'm a little bit behind, so maybe 2.5 days are actually 50-minute lecture days are spent on this project. And then the last week is reserved for reviewing for the final exam. And so it's just kind of a nice break for the students, and they can turn it in during the last week. And since the exam isn't dependent upon the project, it's a good thing to turn in the last week of the semester. Okay, so the instructions for the project is that this is a semi-report, it's not a homework, so it does have its own weight towards the course grade. And they are encouraged to work in groups of 2 or 3 persons, or just one if they want to. However, they have to write up the report individually. If there are 2 responses to one question, okay, you have to deal with people copying from each other. And so, yeah, so I tell them the penalty up front. They write the report as if the reader's a classmate. I think this is really important that you tell them who the prospective audience is. And the report must include 1 to 3 paragraphs of introduction. And, they haven't done a whole lot of reports at this time. So I've learned that we really have to give them details about why you have to write an introduction, what should be covered in the introduction. And then I put in a bunch of questions, so it's not completely all written. And the question part of it, the grader for the course is actually grades it, and then I, or whoever the instructor is, would just grade the introduction and the conclusion. And the conclusion is just what are the main takeaways from the project. And of course, for this problem, we are assuming damping is negligible, no damping. Okay, so the first thing we look at is how to model a system of masses and springs. And so this is the very first question on the project: derive the governing equations for the homogeneous first order system. And I actually just give them verbiage to help them get started, because they're like, I don't know what to say. I don't know. So yeah, so, and then I expect them to carry on. They can use the suggested words that I give them, or they can do their own, and then they just continue on their own. And this really seems to help them get started, at least. And then I have them do checks. Like, once you have a model, you want to just make sure that the model makes sense. You know, if the mass of, you know, if the spring 2 is not there, do you get what you expect to get? And if the displacement between the first mass and the second mass are equal, then the net force should be 0. So I put in several checks that I expect them to do as part of their problem. And then, of course, write it as a system of equations. So this example is 6 equations, 6 unknowns. And if you put in that all masses are 1 and all springs are 1, then they get the following system. And so now the fun begins. Okay, so we get to compare with the real world. And every time I teach this, I have to go out and search and see if we can find software that's easy to use to find eigenvectors and eigenvalues for a system where the eigenvalues are complex. And so, so in this particular case, here are the 6 eigenvalues that you get. And of course, they appear in complex conjugate pairs. And then they have to convert it to get real solutions, and writing it in terms of eigenvalues and eigenvectors. Okay, so now they have this result, and then they're going to watch this video online. And so they can take a look at this. And let me know if you can hear this.
Freedom mass spring system has one natural frequency.
Can you guys hear
and one
this?
Vibrational mode shape. The mass oscillates back and forth, or in this case up and down, at a frequency that depends on the inertia or mass and elastic or stiffness properties of the system. First frequency, the 2 masses move in the same direction at the same time, basically looking like a 1 degree of freedom oscillator. In the second mode of vibration, the 2 masses oscillate in opposite directions, one going up while the other one's going down. At the very center in between the 2 masses is a node, a point that doesn't move at all. A 3 degree of freedom mass spring system has 3 natural frequencies and 3 mode shapes. In the first mode shape, all 3 masses move in the same direction at the same time, with the center mass moving slightly farther than the outer 2. In the second natural mode, the center mass is stationary at a node point, while the 2 outside masses move with opposite phase in opposite directions. In the third natural mode shape for the 3 degree freedom system, all 3 masses alternate in directions or phase. The 2 outside masses move together, and the inside middle mass moves in the opposite direction compared to the outer 2. Hopefully by now you'd be able to guess that a 4 degree freedom system would have 4 natural.
Okay, so I think you get the idea here. And so then after seeing that video, we examine the natural frequencies and the mode shapes, the modes here for this system. And we see for the lowest mode, which appears third here, we have the 3 degree of freedom system where they all move in the same direction, and the middle mass, it moves further than the outer two masses. And for the next highest frequency, the middle node stays still, just like in the picture here, and the outer modes move back and forth. And likewise, for the highest frequency, we have that the middle mode moves in the opposite direction as the first and outer mode. Okay, so they love that when they see this. Okay, so now we can go and discuss what happens in an earthquake. And we're going to model a 3-story building. And as in part 1, we derive the governing systems of equations, 6 equations and 6 unknowns, and be sure to define all variables. And even assuming that all the masses are 1 and the spring constants are 1, we end up with the following system of equations. So again, we have 3 frequencies and 3 mode shapes. And we can go to this video and watch and see what happens. And so this is, let's see if I can, it's going. And so this is just a shaker table, and they're slowly increasing the frequency. And we'll see what happens as they keep increasing it. So this is the first natural frequency. And now we've moved on from the first natural frequency. And it sounds like things are going to break apart, but not yet. Okay, so that's the second frequency. And the system doesn't get to the third natural frequency, which was kind of sad, but that's okay. Okay, so they have that, and what they're asked to do is compare their answers with what they saw from the YouTube video. And if you look at the lowest frequency here, you can see that the mode shapes are 1, 1.8, 2.24. This 1 corresponds with the lowest mass. So they're all moving in the same direction, with the highest mass moving the furthest. And the second highest frequency is corresponds to the highest mass moving in the opposite direction as the first floor and second floor. And so the mode shapes match. And then the question is, okay, well, what about the natural frequencies? I mean, we just put in like what mass 1 and k equals 1 to make life easy. But it turns out that you can compare the ratios of the natural frequencies, the second frequency and the first frequencies, and it is actually very close to the experimental frequency. So it's not completely crazy, right? It somewhat works. So then we let the students go. And the goal is that earthquakes have frequencies of around 20 hertz. And the goal of designing a building is to be sure that the lowest natural frequency is above the natural frequencies of earthquakes. So you want buildings to have high natural frequencies. So our values for mass and stiffness were not realistic. However, we can adjust the masses and or stiffness to see how it affects the lowest frequency. So each student chooses one mass or one stiffness to change that you think will increase the lowest natural frequency. If it does not increase it, that is fine. Report your result and coordinate with 2 other people groups, giving them credit by citing their names that chose a different change and compare the 3 results. And then that's the end of the report. And I've tried as many application projects in differential equations, and this by far has had the most positive results. So this student says this project was difficult, but actually a lot of fun. I found myself working on it for many hours outside of class and not getting bored. I'm confident in my answers for part 1, but I think the 3 second-order equations derived from the spring mass system created out of the building might be wrong or inconsistent in some way. I still can't really read the vectors or general solutions correctly, but I understand that the coefficient of t within cosine xt or I sine xt is the natural frequency. I also get that because we're working with sine and cosine, the solution oscillates, which makes sense. All in all, I wouldn't mind doing another project, although this project absorbed a substantial amount of my time and needed several iterations before I felt it was ready to submit. Also, working in groups isn't something I generally try to do, but it was a good excuse to talk to my classmates. Okay, this project taught me how to apply reducing nth order differential equations to first order equations, then solving using matrix notation. I was able to see through examples how to apply this to a real world application. I also learned that buildings and springs have a similar structure mathematically, being able to use very similar equations. I found it fascinating that adjusting a few variables can make such a large difference. This project helped me understand with some math since it was application of a process. And this next one, from this project, I have learned a lot about spring mass systems and gained a better understanding of how to solve eigenvalues and eigenvectors, as well as another important thing I learned is how to apply what we learned from class into the real world, more specifically with the second part of the project when we applied a spring mass system to a vibrating building, which was supposed to simulate an earthquake. The reason why it's a big takeaway for me is because it shows the importance of learning this topic, since we can use systems of equations, matrices, and natural frequencies to predict how a building will do against an earthquake, whether having thicker walls or different distributed mass throughout the building will cause it to be less or more efficient against the earthquake. And this one, yeah, it challenged you to think, give purpose to the calculations, being able to delve much deeper into a math topic and really try to understand the complexity. Let's see, of all this seemingly uninteresting connections makes me much more passionate about math as a whole. And once those connections start to click, it is a very satisfying experience. I believe this project helps to demonstrate a growth in understanding of my knowledge in math beyond the minimum I usually require from myself, and to actively seek further meaning to it all. So yeah, so I mean, there was not one single student, this is a C, probably D-level student. And overall, this was a fun project. And so, yeah, it was phenomenal. Like everybody was writing how much they enjoyed this project.